acceleration for 8.3 seconds. During that time, it traveled 34 meters and had a final speed of 2.5 meters per second. What was the car's initial speed is the first part. Okay. So let's see, if we have our car and it sees a cop, so let's say the cop is over here. Okay, cop's over here. It sees a cop and it starts braking down. Okay, we know that the initial velocity is unknown, but we know after it braked, the final velocity is 2.5. Okay. We also know that it traveled 34 meters from here to here. Okay. And all of this occurred in a time of 8.3 seconds. Okay. Sometimes I like drawing out a little picture to give you a good visual of what is occurring here. Now I'll make a table because I know this is kinematics. It's one-dimensional motion, and it gave me a bunch of values, so I know this is going to be a kinematics problem. So as always, I'll go ahead and start with my table. I do this the same way every time so that each problem, you can relate each problem to the next problem, and you'll see that most of the problems are the same thing. It's just different scenarios. So in this one, I just plug in what I know, the change in x. Okay, how far did it go? It went 34 meters. Already in SI units, so everything there is good. The initial velocity, I don't know how fast the car was going, but that is what it's asking for. What was the initial speed? So that's my question mark. Final velocity, after it had braked, it was down to 2.5 meters per second. That's my final velocity. Acceleration, I know that it was under constant acceleration, but it doesn't tell me what the acceleration was. And as for time, I know all this occurred in 8.3 seconds. All right, I've got enough to solve. I've got 3 things. I know what I need to solve for, and the one thing I don't care about is acceleration again. So similar to the other problem with the proton. Okay, so I need to solve for something without that a being in it. I need to grab a kinematic equation that has that formula in it. So that one, of course, is going to be the change in x is equal to 1/2 vi plus vf times t. And I start plugging in. Okay, this time we have 34 for the change in x. This is going to be equal to 1/2 vi. I don't know. That's what I'm trying to solve for. So I'm just going to put vi plus vf, so this is 2.5, times t. This one we know what t is, 8.3. So we just have one variable, so again, we just need to rearrange this equation so that it works. Okay. Let's see, if I go ahead and multiply both sides by 2, I can get rid of this half, right? Because half times 2 is just going to be equal to 1. So I'm going to have a 68 equal to vi plus 2.5, and then this is all multiplied by 8.3. Let's get rid of that multiplication. Let's get rid of this 8.3 by doing a division. Okay, and then I'll get rid of this. And then what are we going to have here? I'm just going to put it as 68 over 8.3 is equal to vi plus this 2.5. So to get vi by itself, I'm going to want to go ahead and minus that 2.5 to the other side. Okay, so I should end up with a 68 over 8.3 minus 2.5 is equal to vi. Now, do you speed up when you see a cop, or do you brake when you see a cop? Most likely you're going to slow down. So a speeding car sees a cop and it brakes. So our initial speed should be greater than our final speed if the problem made sense. So let's plug this in and find out. I get, for a VI, I get 69277. I'm going to go ahead and round that. 5.7 meters per second. That's our VI. Okay. And it makes sense. 5.7, they braked down to 2.5 when they saw the cop, so it should make okay sense. For part B for this, what is the acceleration while slowing down? Okay, so for that one, we need to solve out for the acceleration. Now, in the last problem, I said don't use the value that you already have unless you're confident that that everything matches up. I think that's a pretty confident answer. That's in the ballpark of what it would slow down to. It's not anything crazy. So I'm going to go ahead and use that number for part B to determine the acceleration. Okay. Acceleration, could be something as simple as the first problem, right? So we have change in x is equal to initial acceleration plus a times t. Okay, so that's the first equation. It doesn't rely on the final velocity, so we're going to go ahead and use that initial velocity. The distance that it traveled, same problem, remains the same, so 34. The initial velocity, that's what we solved for in the last part, 5.7, so I'm going to go ahead and put that in. Plus the acceleration, that's what we're solving for, so I'm going to leave it as an A, times the time. Okay, and the time was 8.3. So now we need to play the same game. We have an addition going on here. Let's go ahead and get rid of that by minusing 5.7 to the other side, and then we'll divide the whole thing by 8.3 for the time. Okay. Oops, and of course I see a mistake already in my problem here. I put down the wrong formula. Always double check your formulas. This should be the final velocity is equal to the initial velocity times, or plus AT. So we don't want 34 there. My answer would have given me something very, very strange. Could have used that, I guess, as a teaching moment, but let's go ahead and get that changed over. As soon as you see it, make that correction. So final velocity on this was 2.5. Okay, so 2.5 is equal to 5.7 plus A times 8.3. And the reason I caught that is because I was expecting to be a negative number over here. I figured acceleration must be negative if they're braking, if they're slowing down. And 34 minus the 5.7 is going to give me a positive number. So I knew right off the bat something wasn't quite right in here. How does the car speed up and slow down at the same time? So I knew something was wrong. Go back and check your formulas whenever that happens and see if you can figure out where the mix-up is. Okay. So using the correct formula, we get 2.5 minus the 5.7, and instantly that gives us a negative number on this side, negative 3.2, okay, with this minus this. Now what's left here is the acceleration times 8.3, so what I would want to do is divide both sides by 8.3, because that would just get A by itself. Okay, so if I go ahead and I do that, I get an acceleration that is a negative number, and it is something small, so the person didn't slam on the brakes, okay, but they did come to a nice stop. So it is zero, or not a stop, but they did slow down. It is negative 0.386 meters per second squared.